Hello friends, welcome to our YouTube channel. Two-port networks may be described in various ways. Today we shall learn how to describe two-port network using inverse hybrid parameters or simply called G parameters. We shall learn how to draw the equivalent circuit of two-port networks using G parameters. We shall also learn how to determine these G parameters. Finally, we shall solve a couple of numerical problems to learn how to determine G parameters for given electrical networks. An electrical network having one input port and one output port is known as two-port network. Here we can see the block diagram of a two-port network. By analogy with transmission networks, one of the ports is called the input port and the other is known as output port. Each port has two terminals, one for entry and the other for exit. By definition of the port, current at the entry terminal of a port must be equal to that of the exit terminal. We have four variables, two port voltages V1 and V2 and two port currents I1 and I2. Only two of these four variables are independent variables. Therefore, we can express two variables in terms of the other two. Two linear equations are used to relate these variables. Inverse hybrid parameter representation is the dual of hybrid parameter representation. In this method, we express input port current and output port voltage in terms of input port voltage and output port current. The linear equations used in this case are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. These two equations can be written in matrix form as follows. Matrix of I1 V2 equals to matrix of G11, G12, G21, G22 into matrix of V1, I2. The elements G11, G12, G21, G22 are termed as G parameters. They are measured by open circuit test and short circuit test. They are dimension wise mixed type. As the input port current I1 and output port voltage V2 are expressed in terms of V1 and I2, which is the reverse case of hybrid parameters. That is why these parameters are known as inverse hybrid parameters. Now let us draw the equivalent circuit of a two-port network using G parameters. The linear equations used to describe a two-port network using G parameters are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. We have to implement both the equations while drawing the equivalent circuit. Let us first draw the input and output ports and then let us assign the input and output port voltages and currents. Now, if we examine the first equation, then we find it contains two parts. The first part is nothing but a current. So, if we connect an admittance G11 at the input port, then we can realize it. Now, if we examine the second part, then we see it is nothing but a controlled current source controlled by the output port current. Therefore, if we draw a current controlled current source G1 to I2, we can realize this part. So, the first equation is implemented. Now, if we examine the second equation, then we see it contains again two parts. The second part can be implemented by connecting an impedance G22 at the output port. Now, if we scrutinize the first part G21V1, it is nothing but a voltage controlled voltage source. It is controlled by the input port voltage V1. So, let us draw G21V1 a dependent voltage source. Now, we have realized both the equations. So, we have drawn the complete equivalent circuit using G parameters. Hope you shall be able to draw the equivalent circuit on your own now. Now, let us determine G parameters of two-port networks. Some of them are measured by open circuit test and some of them are measured by short circuit test. Let us perform the open circuit test first. For this purpose, a voltage source will be connected at the input port and the output port is kept open. We shall connect two voltmeters to measure the port voltages and an ammeter to measure the input port current. As the output port is kept open, I2 becomes 0. The linear equation we use to describe two-port network using G parameters are I1 equals to G11V1 plus G12I2 and V2 equals to G21V1 plus G22I2. When I2 equals to 0, the first equation reduces to I1 equals to G11V1. Therefore, G11 equals to I1 by V1. G11 is termed as input admittance when output port is open circuited. This is measured in mho. When I2 equals to 0, the second equation reduces to V2 equals to G21V1. Therefore, G21 equals to V2 by V1. G21 is known as forward voltage gain when output port is open circuited. Now let us perform short circuit test to determine G12 and G22. Now we connect a voltage source at the output port and the input port is short circuited through an ammeter. Therefore, V1 equals to 0. Now we connect an ammeter at the output port to measure current I2 and a voltmeter to measure V2. The linear equations used to describe two-port network using G parameters are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. When V1 equals to 0, the first equation reduces to I1 equals to G12 I2. Therefore, G12 equals to I1 by I2. G12 is termed as reverse current gain when input port is short-circuited. When V1 equals to 0, the second equation reduces to V2 equals to G22 I2. Therefore, G22 equals to V2 by I2. G22 is known as output impedance when input port is short-circuited. It is measured in ohm. Let us solve a couple of numerical problems. First, we shall find G parameters for the T network shown. Let the input and output port voltages be V1 and V2 and the mesh currents be I1 and I2. Applying Kirchhoff's voltage law, in loop 1 we get V1 equals to ZA plus ZC into I1 plus ZC into I2. From loop 2 we can write V2 equals to ZC into I1 plus ZB plus ZC into I2. Now let us open circuit the output port, that is I2 equals to 0. So from equation number 1 we can write V1 equals to ZA plus ZC into I1. Therefore G11 equals to I1 by V1 equals to 1 upon ZC plus ZA. Now from equation number 2 we can write V2 equals to ZC into I1 as I2 equals to 0. Therefore we get G21 equals to V2 by V1 equals to ZC by ZC plus ZA. Now let us short circuit the input port, that is V1 equals to 0. Therefore from equation number 1 we can write 0 equals to ZA plus ZC into I1 plus ZC into I2. So we get G12 equals to I1 by I2 equals to minus of ZC divided by ZC plus ZA. Using this expression in equation number 2 we get V2 equals to ZC into minus ZC by ZC plus ZA into I2 plus ZB plus ZC into I2. That is equal to ZA-ZB plus ZB-ZC plus ZC-ZA divided by ZC plus ZA into I2. So we get G22 equals to V2 by I2 equals to ZA-ZB plus ZB-ZC plus ZC-ZA divided by ZC plus ZA. Now we have to find G parameters for the resistive network shown. Let the input and output port voltages be V1 and V2 and the loop currents be I1 and I2. Applying Kirchhoff's voltage law, from loop 1 we can write V1 equals to 4I1 plus 3I2, and from loop 2 we can write V2 equals to 3I1 plus 5I2. Now let us open circuit the output port, that is I2 equals to 0. Now from equation number 1 we get V1 equals to 4I1 and from equation number 2 we get V2 equals to 3I1. Therefore G21 equals to V2 by V1 equals to 3 by 4 and G11 equals to I1 by V1 equals to 1 by 4 mho. Now let us short circuit the input port, that is V1 equals to 0. Now from the first equation we can write 0 equals to 4I1 plus 3I2. Therefore we get G12 equals to I1 by I2 equals to minus 3 by 4. Using this relation from equation number 2 we can write V2 equals to 3 into minus of 3 by 4 I2 plus 5 by 2. That gives us 11 by 4 I2. Therefore, G22 equals to V2 by I2 equals to 11 by 4 ohm. We have to find G parameters for the pi network shown. Let the input and output port voltages be V1 and V2 and input and output port currents be I1 and I2. Let us mark the nodes 1 and 2. Applying Kirchhoff's current law at node 1 we can write I1 equals to YA plus YC into V1 minus YC into V2. And from node 2 we can write I2 equals to minus YC into V1 plus YB plus YC into V2. Now let us open circuit the output port, that is I2 equals to 0. From equation number 2 we can write 0 equals to minus YC into V1 plus YB plus YC into V2. Therefore we get G21 equals to V2 by V1 equals to YC divided by YB plus YC. Using this relation from equation number 1 we can write I1 equals to YA plus YC into V1 minus YC into YC by YB plus YC into V1. Therefore we can write I1 equals to YA YB plus YB YC plus YC YA divided by YB plus YC into V1. We get G11 equals to I1 by V1 equals to YA YB plus YB YC plus YC YA divided by YB plus YC. Now let us short circuit the input port, that is V1 equals to 0. Therefore from equation number 1 we can write I1 equals to minus YC into V2. And from equation number 2 we can write I2 equals to YB plus YC into V2. Now we get G12 equals to I1 by I2 equals to minus YC divided by YB plus YC, and G22 equals to V2 by I2 equals to 1 upon YB plus YC. We have to find G parameters for the resistive pi network shown. Let the input and output port voltages be V1 and V2 and input and output port currents be I1 and I2. Let us mark the node 1 and 2. Applying Kirchhoff's current law to node 1 we get I1 equals to V1 by 1 plus V1 minus V2 by 2. That reduces to 3 by 2 V1 minus 1 by 2 V2. Now let us apply Kirchhoff's current law to node 2. Therefore we get I2 equals to V2 minus V1 by 2 plus V2 by 3. That reduces to minus half V1 plus 5 by 6 V2. Now let us open circuit the output port, that is I2 equals to 0. So from second equation we get 0 equals to minus half V1 plus 5 by 6 V2. Therefore G21 equals to V2 by V1 equals to 3 by 5. Using this expression In equation 1, we get I1 equals to 3 by 2 V1 minus 1 by 2 into 3 by 5 V1. That is equal to 6 by 5 V1. Therefore, we get G11 equals to I1 by V1 equals to 6 by 5 ohm. Let us short circuit the input port, that is V1 equals to 0. From equation number 1 we get I1 equals to minus half V2, and from second equation we get I2 equals to 5 by 6 V2. Therefore, G12 equals to I1 by I2 equals to minus 3 by 5, and G22 equals to V2 by I2 equals to 6 by 5 ohm. Let us find G parameters for the resistive network shown. Let the input and output port voltages be V1 and V2, and the mesh currents are I1, I2 and I3. Applying Kirchhoff's voltage law to the loop 1, we get V1 equals to 3I1 plus I3, and the second equation we get V2 equals to 2 times I2 minus I3. From the middle loop we can write 0 equals to I1 minus 2I2 plus 5I3. Therefore, we get I3 equals to 2I2 minus I1 divided by 5. Using this expression from equation number 1, we get V1 equals to 14 by 5 I1 plus 2 by 5 I2. And from the second equation, we get V2 equals to 2 by 5 I1 plus 6 by 5 I2. Let us open circuit the output port, that is I2 equals to 0. Therefore, from the first equation we can get V1 equals to 14 by 5 I1. Hence, G11 equals to I1 by V1 equals to 5 by 14 more. From equation number 2, we get V2 equals to 2 by 5 I1 when I2 equals to 0. Therefore, we get G21 equals to V2 by V1 equals to 1 by 7. Let us short circuit the input port, that is V1 equals to 0. Now from equation number 1 we get 0 equals to 14 by 5 I1 plus 2 by 5 I2. Therefore we get G12 equals to I1 by I2 equals to minus 1 upon 7. Using this relation, from equation number 2 we can write V2 equals to 2 by 5 into minus 1 upon 7 I2 plus 6 by 5 I2. That is equal to 8 by 7 I2. Therefore, we get G22 equals to V2 by I2 equals to 8 by 7 ohm. So, today we have learned how to describe a two-port network using inverse hybrid parameters. We have also learned how to draw the equivalent circuit using G parameters. We observed how to determine G parameters performing open circuit and short circuit tests. Finally, we have solved a couple of numerical problems to determine inverse hybrid parameters for given electrical networks. That is all I have for you today. Hope this lecture has been useful for you. If you have any question or suggestion, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.